I'd like to thank you all for choosing to spend a little bit of your morning with us at this workshop. I'm Norm Eygenraam from Multi-Shelter Solutions in Palmerston, Ontario. And with my 40 plus years of industry experience, I guess the show management thought I had something of value to contribute to the topic that we have this morning. Now, one thing I'm just going to mention, because I wasn't aware that there was 4 screens here, I am going to be pointing out different things on the screen, and obviously I can't be both sides, so maybe some of the people that are sitting on that side would choose to be moving a little bit this way so that they can see a little bit your option. So just before the owner of this particular building gave me the signed contract for this particular building, he told me, sort of in the way that he wanted to get the prices cheaper, he said, this concept is way over-engineered. Luckily for me, I had given him an extremely detailed step-by-step as to the only way that this particular package was going to work. Well, unfortunately for him, he chose to file that paper with the invoice and the quote and all the rest of the paper. Just a little cartoon that I came across that sort of emphasizes the importance of being on the same page and having proper communication. If you look at the bottom right-hand side, what the customer was after was actually quite simple. And all the rest of the pictures sort of depict what the so-called experts had in mind for that simple project. I do spend a lot of time assessing customers' needs and their situation to come up with a good solution, and because many times what a customer has in mind for these simple little perfect little add-ons actually just magnify what Mother Nature is going to throw at the particular building. This is an upside down greenhouse. That's sort of an unfortunate example of what happens when a customer has something in mind they want to do without saying something. And you have no idea how I almost cried when I saw this particular picture the customer sent me. I just said, like, why didn't you tell me? Because all of this effort that they had put into bringing this building to this particular point, now in a matter of a few seconds was upside down. You've got, here are the anchor posts. This part here is the roll-up side, and then it goes like this. You've got the cross ties. The whole thing is just upside down. Now I'm going to be coming back in a few minutes to this picture when we're going to be discussing what these people were thinking, what went wrong, and how to make sure you don't set yourself up for that. Today's workshop is going to be an expansion of part of the one that I did last year. Greenhouses 101 from last year was all about the different choices that you had that you should be aware of before you buy a structure and the consequences of some of those choices. We did touch on the 3 forces that affect a greenhouse, both down, up, sideways, and we had a bit of aerodynamics and weather thrown in for good measure. That particular workshop was recorded at that time and is available on our website, multisheltersolutions.com. So greenhouses 202. how to improve the odds of your greenhouse staying put in its original shape, in its original condition, and with a minimum of stress. The reason I add minimum of stress is because so many people put something up and then just spend the next number of years worrying about whether it's going to stay there. The idea here is to figure out what the potential problems are and to minimize that stress. So over the next 40 to 45 minutes, I am going to be sharing some of my 40 plus years industry experience to hopefully get you to minimize the risk of a greenhouse failure. The outline of this presentation is on page 30 in these books here. When I checked it out, there isn't enough room there for notes, so you'll have to have your own room for notes. If you're planning a structure, hopefully you're going to learn some stuff to prevent problems in the future. And if you already have a building, hopefully you're going to also pick up some things so that you can minimize the risk. There will be ample opportunity for questions at the end. Now, before I really get started with this presentation, one thing that I really want to emphasize. First of all, in the essence of time, some concepts are being simplified. So please be aware that some things are more complicated than I might present them. The other thing is, if you have a similar situation to what I'm describing or a similar problem, don't assume that all problems and all solutions are created equal. Please ask. So there are basically three forces that any building has to deal with. You've got down, up, sideways, and just some aerodynamics for fun. The down force is most of the time associated with snow load. The uplift and the lateral shift are two separate forces, but are very much intertwined. And these forces are the result of a whole assortment of weather and aerodynamics. The snow load issue is the first thing that most people ask me about. The question is, what kind of snow load will this building take? That would sort of seem like the obvious way to start, but I really think that we need to cover a few of the basic principles of engineering before we get started. I'm not going to bore you with a whole lot of technical jargon, but I do think it's important that you realize some of the basic principles that are going to be affecting your building. In most cases, understanding the situation is 90% of taking care of it. And it is definitely a situation where ignorance is not bliss. This particular slide, this is what we submit to an engineer when a building is going to be evaluated. All of these coordinates that are listed here, that allows the engineer to load the model of this particular building into his software so that once that is completed, the software can sort of do this mock weather on a particular building. During the evaluation, if you're coming into an area where there is stress or failure, then red flags will come up. So then we would go back, assess what actually failed, and then take steps to beef that particular area up so that, and then do the test again. And once the whole test is done and you've stayed within all the parameters, then the engineer will officially put his stamp on the piece of paper, and that's what the building departments want to see. So how do loads increase and stresses increase? From an engineering perspective, when you go bigger, things have a snowballing effect. When you increase something by 50%, you're actually getting 100% roughly increase in the load, the stress on that particular function. So now the building on the left is 20 foot wide with roughly a 10-foot peak. The building on the right is 30 foot wide with a 15-foot peak. So the width is an increase of 50%, which means that your snow load increase on that particular package is roughly 100%. You've got the same thing when you take the height. Going 15 feet from 10 feet is roughly a 50% increase in the height. So you're getting 100% increase in the wind load. Now, when you put those two loads together, then you're getting very quickly, you're quadrupling the stresses that are on a particular building, and that's why when you look at the buildings that are out there, the little buildings have very light material and they get away with it, but as you go bigger, it very quickly gets a whole lot bigger, a whole lot heavier, and correspondingly, they get more expensive. So this is not to, again, bore you with details or confuse you or anything, but I just want you to realize how quickly things can change, and you could potentially be on the wrong side of a disaster. Anchoring is the foundation of your building. There simply is no such thing as too many anchors. Proper anchoring is the foundation of getting your building to stay put, stay where you intended it. Proper anchoring is what prevents the building from settling under snow load. Proper anchoring is also what hangs onto the building so that it doesn't become a parachute that ends up in the next county. Proper anchoring is also something that stabilizes it so that it doesn't start moving over to your neighbor's property. There are many components to proper anchoring. There are right ways to anchor, and there are wrong ways. One of the very common anchors that are being used for these structures is what's called a T-post. A T-post is extremely hard steel, so it is good even if you're dealing with rocks and very hard ground. But a T-post is slippery. So when you pound it into the ground, there really isn't that much holding power. But because it is such hard steel and it resists bending, if you put one anchor post like this, and you put the next anchor post like that, now the anchor posts are working in a buddy system, and they will back each other up. This one wants to lift this way, this one wants to lift this way. Well, obviously it can't go both ways at the same time. So something that might have like 50 pounds, let's say, of holding power by itself. Now the two of them, they'll actually magnify each other, and between the two we'll have 500 or even 1,000 pounds of holding power. So it really quickly does the job better for you. Another thing, like this is another typical anchor post, and one of the things you need to remember is that the friction that is exerted on this is what you have, what gives you holding power. These posts are relatively smooth, so by themselves they don't have a lot of holding power. Adding concrete to the bottom is going to give you a lot of extra weight, and it's going to give you the extra friction, but it also adds to the permanence of the building, which is something you might not want. It also increases the cost and the work. When a structure is sitting on the ground, all of the loads are directed down to the ground. Something that is mounted at the ground is the most stable and secure and will resist shifting. Once you put something up, a building up on something, now all of a sudden you've changed all those load transfer points. Instead of being at the ground, you're now a certain level up. You have to remember that by raising something up, depending on the size of the post, there's leverage that comes into play. If there is any kind of wiggle room, Mother Nature is just going to work on that until your building gets destroyed. One of the things that is asked to me very often is, okay, what size post do I use and how far apart? Obviously, the reasoning behind the question is, you know, the smallest post, the farthest apart, is the cheapest for the application. Everybody wants to save money. What you have to remember is the total surface area that you have on that post. That is your resistance to the thing leaving. In most cases, when you have more small posts rather than fewer big posts, you're getting more holding power. This is a little miniature version of what these posts look like. Because, again, there's not a lot of friction on the post itself, the ideal way of adding to the holding power is to put these cleats on the bottom of the post. Put two going this way, two going the other way, and they're fastened to the side of the post. Now, when you stand that in the bottom of the hole and you fill that with dirt, now there's a lot more holding that down than just the friction on the side of the post. Now, the next potential problem is there's not much surface area here to keep the post from pushing out or pushing in. So that's why it's recommended that just below grade, now this is going to be backfilled here, and this board, the idea for putting it on the side like that is that you will then backfill against it, drive over it with a tractor or something else. So now there's a lot more resistance to those posts leaning out. Another thing that a lot of people don't really take a minute to think about is, where does all the water go? In this particular slide, this is a 30-foot wide building. which means that that building sheds 15 feet of rainfall each way. So now this area along the side here, on either side, it gets 15 times as much rain as all of the rest of that property. Unless you've got really good drained soil, that's not going to have much holding power. Now in this particular case, this customer also, he wasn't taking any chances. So what he did was he put these braces on the side. Now these braces actually have a twofold benefit. One, they stabilize the top of the post, and also because these things go into the ground, there's actually additional holding power there to keep that building from leaving. I mentioned I was going to come back to this. And so what were they trying to accomplish and what went wrong? Many people have this idea for a greenhouse that they would like to insulate the base on either side of the structure as a way of keeping the frost out. It's this eternal battle of keeping the cold out but making sure that you still get all the proper light. That's what these people set out to do. Now, aside from the fact that it's an awful lot of work, you're also, by putting, and this is insulation here, so they dug a trench on either side of the structure to put this insulation in right beside the anchor posts. So in addition to all that work, all of that soil that was around those posts had been freshly disturbed. No amount of packing it, unless you're going to be back and forth for like a long, long time with a tractor, would get you back to what that was before you started digging. So if you look closely on this part of the post here, it's still clean. That part there is what was actually holding it. Now, if you remember back to the previous slide, I talked about the extra rainfall. In this particular situation, this was a 20-foot wide building, so you're getting 10 foot more on either side. So not only does that structure have 10 times as much rainfall on it as what the rest of the property, this is disturbed soil. The other thing that they were sort of counting on was the fact, okay, it's winter, ground is going to freeze, it's going to have more holding power. Now, but because of the fact that they had the insulation there, also this was a greenhouse, which was a heated greenhouse, so they weren't getting any frost to give them extra holding power. So now all that you need is a combination of some rain, a good windstorm coming from the right direction, and this is what happens. When somebody comes to me and says, you know, I want to insulate, I stop them. Like, I want people to get away from the idea of putting insulation into the ground like this. What I suggest instead is that you slightly grade the soil on either side of the building and just firm it up. You lay the insulation on top of that and then just backfill with a fine layer of gravel. So not only do you still get all of the benefits, you don't have nearly as much work, but because you've got that extra slope there, you're going to get extra rain being shed away from the building, which is going to help the anchor post. Also, you're going to get a really extra good buffer of weed control because the gravel on the insulation keeps the weeds 2 feet away. One thing I want to say, before we leave this slide, one thing that I felt really good about just knowing how the farming community in their neighborhood came together and helped them out. It really reinforced in my mind how farmers are collaborators a lot more than competitors. So how much snow will a building take? Well, that sort of depends on a whole bunch of things. The winter of 2013, 2014 was a worst case scenario that I had been talking to people about for many, many years. December the 23rd, 2013, we had a really nasty ice storm. That was followed up by gradually getting colder and lots of snow. So the snow was freezing to the structure. Then by mid-January, we had a mild spell, we had rain. When you have that scenario, in a half an hour with like 1 or 2 centimeters of rain, you can double, triple your load on the building just like that. The final icing on the cake for this was that right after that combination, it got very windy. And now you got all this extra load, the building is barely standing, and then it starts being rocked. And the wind just magnifies it. From January to April of 2014, there were more buildings that came down than I had seen in the 40 plus years of doing greenhouse construction. Removing snow and ice is a very simple thing that I will come back to in a few moments. One of the things that very much surprises me about these greenhouses is how much they can take when the load is balanced. The flip side of that, I'm equally amazed at how little will cause a problem if it's all on one side. Now, the owners in this particular situation were actually very fortunate that they caught this situation before it was a total failure. And so what they did was they put 2x4s underneath this, and they definitely could have done it a little bit more effective by having them on the right angle. But what this allowed them to do was to use the structure through the spring season and get the use out of it, and then plan for a rebuild in the summertime. When you do a rebuild in the summertime, it's always a lot cheaper and it's a whole lot easier on the nerves. One other thing I was just going to point out, like there doesn't seem like a whole lot of snow over here. This picture was taken about a month after the fact. It wasn't that minor amount of snow was not what caused the problem. One thing that you do need to keep in mind when you're considering uneven snow load is how the snow got there. When you've got a greenhouse in line with another building that is quite a bit taller, you're going to get drifting snow that is coming off of the tall building and potentially onto the greenhouse. And when you've got all these different wind patterns, things are going to come together in a very funny way. That is definitely a potential problem. The other thing is if you have your greenhouse parallel to a taller building and it is close enough that if you have sliding snow coming off, you know, a chunk of 100 pounds of snow might not be much for a particular building, but it slides off and hits it with a force of 400, 500 pounds, it would potentially do some damage. This particular building is a 30-foot that was modified to 34 feet wide because the customer wanted to have more floor space. Generally speaking, when it comes to greenhouses, more floor space means that you can have more production. More production means you're getting a higher return for the same investment. Some things you need to keep in mind when you're doing that is that in this scenario, by going 13.5% wider, you are also increasing your snow load by almost 30%, which is definitely something that you need to keep in mind. Another thing is that when you're going wider like this, the sides are no longer straight up and down, which means that when the snow piles up beside it, you're going to get a lot more lateral push than if the sides are straight up and down and the weight is down onto the ground. Now, another thing is, in this particular thing, because we were making the structure wider, we did add the cross ties to it. Cross ties are a way of stabilizing the building, because the logic is if the sides can't go out, the top can't come down. So it definitely does stiffen the building. Removing snow and ice properly. I cannot stress enough the importance of staying out of a building that is severely stressed. If there are visible broken parts or you're hearing groaning and creaking, it is not worth the risk of injury or even worse to try and save the building. There are some simple ways though of removing the snow. One thing, just thinking back to that last slide for a minute, when you've got a building that is shaped like this and it sheds the snow that is on the side is actually reinforcing the package to a certain extent. So if you need to remove the snow from the top,